As it's just past 1 o'clock, I think we'll start anyway. And just to note that this webinar is being recorded. It will be available on the Power Energy and Clean Technologies website. It will also be linked to the iHub website for people to view, and a copy of the presentation will also be on that website. So I won't be speaking to detail to all of the things on each of the slides that I'll show you. Okay, so good afternoon everybody. My name's Wendy Miller, and today we'll be talking about the Living Lab test facilities that are being instigated in Queensland. Let me see. So the Living Labs are part of the Innovation Hub for Affordable Heating and Cooling, just known colloquially as the iHub. And the parties of the iHub are the Australian Institute of Refrigeration, Air Conditioning and Heating, CSIRO, QUT, Uni of Melbourne, Uni of Wollongong, and industry, of course. The general objective is to support the broader HVAC and refrigeration industry. And a disclaimer right at the beginning that the iHub has received some funding from ARENA, the Australian Renewable Energy Agency, under the Advancing Renewables program. So anything that I say today is not necessarily the view of ARENA or the Australian government, and they accept no responsibility for any of the information that I say. So the iHub project, as what it's known collectively in the industry, and the part that's funded by ARENA, consists of three main initiatives or activities. So these are in the top right hand of the slide. So there's the Smart Building Data Clearinghouse that is led by CSIRO, Integrated Design Studios led by the University of Melbourne, and Living Laboratories led by QUT and University of Wollongong. And it's this activity of the iHub that I'm focusing on today. But information about all three activities and projects that are happening within all three activity streams can be found on the iHub website. And in particular today, I'm not also speaking about all the living laboratories, but just specifically the healthcare laboratories and the ones that are in Queensland. There are two additional laboratories, a healthcare laboratory in New South Wales and a schools living laboratory in the ACT. I will not be covering those in the talk today. But generally the purpose of the Living Laboratories activity stream is to provide a live building and operational buildings that can validate new and emerging technologies or programs that can have an impact on the integration of renewable energy, energy efficiency and HVAC systems. So can we add value to renewable energy? Can we change energy demand, etc., etc.? Two living labs are being established in Queensland, and I'll speak about both of those. In addition to establishing the living labs, ultimately the aim is to be able to quantify the performance of new and emerging technologies and see what the benefits of those technologies are to these specific buildings and to these building typologies nationwide. Part of that requires us to look at what sorts of benchmarks and key performance indicators are currently used to look at energy use in healthcare buildings, and what new ones will we need in order to be able to quantify performance of renewable energy and HVAC systems, for example. And part of this program also ties into an international program that's looking at resilient cooling. We'll be talking through all of those topics today. Globally, the healthcare sector accounts for approximately 4.5% of global net CO2 emissions, and 29% of these emissions are directly related to healthcare facilities and vehicles, as opposed to other parts of the healthcare supply chain, such as pharmaceutical and medical equipment production. And energy use accounts for more than half of the sector emissions. So energy, healthcare is a big contributor to global greenhouse gas emissions. the top 10 healthcare emitters, according to this report that was released last year, are shown in column 2 of the table here, and no major surprises there. Australia comes in 10th in terms of emissions from our healthcare sector. And the emission in column 3, we have the countries by general emissions, and it's more or less the same set of countries that have high healthcare emissions also have high general emissions. And these 10 countries that have the highest healthcare emissions are shown in this circle. 10 countries emit, in essence, about account for 75% of the global healthcare emissions. Another way of looking at that data is looking at healthcare emissions per capita per country. And Australia, Canada, Switzerland and the United States are the highest emitters per capita from their healthcare system compared to other high emitters, high average, low average and the rest of the world. So this data points out, first of all, that healthcare is a major contributor to greenhouse gas emissions, and secondly, that Australia is a major contributor to that sector. So how do hospitals, and most of that is related to, or at least half of that is related to energy, so how do hospitals currently indicate how they use energy? So we've undertaken an international scan of literature, and the most common key performance indicator used is energy use intensity, so EUI, per floor area, so kilowatt hours per square metre. And a number of publicly available studies indicate that this number may be anywhere between mid-400s, so 445 per kilowatt hour per square metre is considered by the National Health Service in the UK as a good benchmark. In the USA, a study of over 3,000 hospitals in 2013 found that the mean intensity was nearly 1,500 kilowatt hours per square metre. So there's quite a range of benchmarks here. Some of the other indicators that are in some of these reports include the energy use intensity per full-time staff, per staffed bed, per floor area relating to the cooling degree or heating degree days, or per MRI per square metre. So this range of indicators shows several things. First of all, most reports use this first one because my summation is that it's a fairly easy one to report. What's the total hospital energy use? What's the total floor area of a hospital? And just report on that. But there's also an indication that, as well as the size of a hospital, the number of staff, the number of patients, the climate, and the types of medical equipment that are in those hospitals can also have an impact on the energy use. So we want to find out more detail, we need to find out more detail in order to be able to find what solutions can we have to make hospitals less greenhouse intense in their energy use, and also to enable HVAC energy efficiency and renewable energy integration. So some of this breakdown occurred in the 2012 USA study. So looking at, again, the over 3,000 hospitals, so by energy source, so across their hospitals, just over half of the energy use in a hospital was allocated to electricity, followed by natural gas, with smaller amounts for fuel oil and district heating. Or you can break down the energy use by the end service that it provides, so space, heating, ventilation, cooling, etc. So this pie chart shows again that HVAC systems account for more than half of the use of these US healthcare buildings. In India, a study was comparing the energy use intensity between public hospitals and private hospitals. So the two box plots at the top of this, this chart show the number of beds and the kilowatt hours per square metre in public hospitals compared to private hospitals. And the bottom two graphs are showing kilowatt hours per bed per year in public versus private. Notice that there is a difference, but this report didn't indicate what might be the contributing factors to that difference. Is it the level of care or the medical conditions that are treated in private versus public hospitals? Is it the indoor environment of the public hospitals compared to private hospitals? So these data just at this level show that kilowatt hours per square metre as a key performance indicator has limited usefulness. The table at the top is what we've been able to glean from international research regarding the range of kilowatt hours per square metre from China up to the US in rank order, and showing, for example, Australian regional hospitals at about 460 kilowatt hours per square metre, capital city hospitals slightly less. But none of this data tells us whether these hospitals are energy efficient or not, whether they're meeting benchmarks or not, and what services are being provided by what energy sources under what conditions. And a range of variations will impact on this kilowatt hours per square metre, and those variations can include the climate and cultural expectations regarding indoor climate, the age and energy efficiency of the building and the infrastructure and the equipment within the hospital, the degree of medical specialisation and healthcare provided, the building size and configuration, and also national and regional healthcare budgets. For example, in some countries there is barely sufficient money to provide the healthcare, let alone an indoor environment that might provide some additional cooling and ventilation. So we need to understand what are some of the variables. An interesting study in China was looking at the seasonality of energy use in hospitals across 4 different climate zones. So the blue and the red showing climate zones with hot summers, the green and purple showing climate zones with the cold summers. Notice that the monthly energy consumption profile is quite significantly different for colder climates than what it is for hotter climates. The difference between the summer and the winter months is much more pronounced in hotter climates than in colder climates. A study of UK medium and large general acute hospitals tried to determine then how is the energy use divided up in different departments within a hospital. So this graph is showing the base load and the peak load of different departments. So from theatres, wards, medical imaging, laboratories, day clinics and other. Notice that the difference between base load in watts per square metre and peak load for theatres and imaging is much higher than between wards and laboratories, for example. So it's obvious from this graph that different types of areas within hospitals are more energy intensive than others and vary depending on what their workload is at any particular time. This same study then looked at when those departments were using their energy, so whether you divide the data up by all days, so 365 days a year, or whether you look at it from a weekday versus a weekend day. And that also shows differences that theatres, for example, have less work on weekends than on weekdays. Wards, as expected, are pretty static across weekdays and weekends. More imaging happens on weekdays than on weekends. Laboratories are slightly less on weekends than on weekdays, etc. In addition to looking at what are some of the current KPIs in healthcare, we also looked at what are some of the healthcare trends that are happening around the world. And we identified 4 key trends that we think can have an energy implication. First of all, there is a blurring of lines regarding what is a hospital. That a lot of facilities now are not just a hospital, but they can be a place where medical, surgical and allied health services are provided, as well as general community health, retail, research, and in some regional areas, it's also the residential aged care facility, for example. So defining what is a hospital and what other things is very blurry. The second is determining are hospitals the appropriate or only way of providing medical care. And Denmark is a good example of this. As a nation, they have systematically started closing hospitals and only keeping open sufficient hospitals that are only for critical and specialised care. And most medical services are provided in local clinics with home aftercare. The third healthcare trend is regarding technology, and this has both benefits and disadvantages from an energy perspective. As medical diagnostic equipment becomes available, this equipment is often very energy intensive, so the more medical equipment or the more sophisticated the equipment, the energy use of a hospital can go up. At the same time, however, more and more energy efficient building services, so air conditioning systems, for example, are being developed. The fourth major trend refers to electrification, and this will vary from place to place around the world. In some countries, and Australia may be one of these, the potential for displacement of gas with all electric building services. And the second is the potential for electric transport to also become part of the building services remit, because a lot of healthcare services also have large vehicle fleets because of the community care that they provide. So what opportunities does this present for incorporating fleet energy into building energy services? Aged care homes have a somewhat similar picture. A study in the EU of 100 care homes across 10 countries was looking at what energy sources those care homes rely on, and from the table on the top, you can see most care homes rely on at least 2 different sources of energy, and that varies a lot depending on what resources each country has access to. And the 4 key performance indicators that this study focused on to be able to compare the energy intensity of all of these care homes were kilowatt hours per square metre, kilowatt hours per resident, kilowatt hours per heating per square metre, and heating per resident per year. But that in itself is not particularly helpful either. But in Australia, there are very, very few published, publicly available reports about energy use in aged care facilities. An audit of 15 residential aged care homes for the New South Wales government just broke down the energy use. So about 44% of the energy use in these homes was for heating and cooling, just under 30% for lighting and other. Again, it shows the high use for heating and cooling. In Tasmania, a report of 9 homes was looking at the variation in the kilowatt hours per bed amongst the 9 facilities shown across the bottom. And notice that the difference between this facility and this facility, again, about a 40% difference. But we don't know what things accounted for those differences. So what might account for them? One thing that might account is the model of accommodation. So residential aged care in Australia has essentially 4 different types of accommodation. One are independent living units that are essentially fully self-sufficient apartments, 1 or 2 bedroom apartments that are typically occupied by a single elderly person, sometimes a couple, and they live relatively independently and select the level of care that they require. The second model is hostels, and this was became quite popular in the 1980s perhaps. They're essentially share homes with independent bedrooms and common shared spaces. The bathrooms may be ensuite or may be shared, and there's a small number of residents per hostel. That might be 10 to 15 residents, for example. Nursing homes are the older style hospital ward-like buildings, and the newer modern residential aged care, I tend to see them more as like a resort style accommodation where each resident has their own room and ensuite, and then there's a variety of shared facilities and full nursing care is provided. So how is energy, how much do we know about how these facilities use energy? A study that QUT did of 80 independent living units in a residential aged care facility in Brisbane in 2016 was looking at the daily electricity use, so kilowatt hours per bed over the different months. So this is the average across all 80 units. Notice that the usage is higher in February and in June, July, and the shoulder months of April, May, September, October. So we have a ramping up of cooling needs, a ramping down, a ramping up of heating needs, and a ramping down. The site peak demand for this facility as well shows a similar thing with, but notice that the summer cooling peak is higher than the winter heating peak, but we still have obvious shoulder seasons. The other interesting thing to see is that the different load profile of a August today compared to a, which is in the dotted line, and a February day in the yellow line, that a summer peak demand day, for example, has a single peak late in the afternoon, which is almost double what the demand during most of the day is. Whereas in winter at this site, there were two peaks, one in the morning, starting at about 7 a.m. and another one at the end of the day. Another way of looking at energy consumption is to look at a portfolio use. So this is Bolton Clark is a residential aged care provider with numerous facilities across Australia. This is the pie chart on the left is their annual energy in gigajoules for their facilities, showing that electricity is by far the greatest energy use, followed by gas. But notice the high percentage of vehicle fuel, so 13%, and what would happen if that 13% was then incorporated into the electricity use. When looking at a range of Bolton Clark facilities, so this graph on our right, looking at the kilowatt hours per bed across a range of facilities, notice that the variance is between the low of around about 15 kilowatt hours a day and a high about one of the highest at about 3 times that. So just looking at kilowatt hours per day is not enough to determine whether a facility is being energy efficient and optimised. But what we do know is that the energy consumption of these aged care facilities is relatively consistent year to year. So this graph is showing 3 different facilities, Facility A, Facility B and Facility C, and that there is not much variation in the kilowatt hours from year to year. The one in the middle shows a drop for 2018, and that's when this particular facility changed the connection, the mains connection to the network. We also know by looking at sub-circuits, in-depth sub-circuits of 2 aged care facilities in Brisbane, that the energy load is highly seasonal for cooling. So both of these facilities in Brisbane have very high cooling demands, which are roughly 3 times what the HVAC demand in June is, for example. The additional thing that we know is that in aged care facilities that the energy intensity can be related back to either the resident or to staff. So some of the energy use is related to air conditioning loads within resident rooms that they have control over, and some of the HVAC loads are related to common areas where typically it's the staff members who have control over that use. So what does all of that mean? What is it that we could analyse, and what KPIs could we use? So we could try to understand the energy use by category, so what loads or tasks or appliances are using the energy, and those KPIs can help us to identify energy efficiency initiatives. We can try to understand who has the control, or what is the end user doing regarding the energy, in order to be able to understand energy user needs and behaviour. We can try to understand the load characteristics of the energy, so what energy use is deferrable, interruptible or variable. Can we have a demand response system? Can we have predictive control? Can we have different market mechanisms to trade? But we also need to understand the building use and the building characteristics. So what types of services are offered within the buildings? Is it just accommodation? Are there services such as kitchen and laundry, or are those services outsourced to somewhere else? Are there office space? Are there retail spaces? And what are the energy associations that can link to some of those different spaces? In addition to all of that, a separate but a connected piece of work relates to the International Energy Agency that's focusing on resilient cooling in buildings. So most of our buildings and our thermal comfort models for designing the indoor environment of buildings, the design of our HVAC systems and the design of our power systems relate to historical weather data, mean historical weather data, averages, but as the climate gets warmer, what we're going to have is much more hot weather and more record hot weather. So this annex is focused on what cooling solutions will be resilient in this context. And to do this, the first part of the work that this group, there's about 20 countries that have signed up to this work, and it's been going for about 10 months now, is to first of all look from a disaster management perspective, what would it mean if we couldn't cope with those things? And disaster management looks at a scale of things depending on how local or national or international an event is and what resources are required to manage it. So the scale goes from an emergency level to disaster, catastrophe. It's a bit like, catastrophe is like a pandemic as opposed to just a localised infection. And in understanding the disaster management process, it helps us understand what do we need to do in order to be able to make sure we have resilient cooling. So what do our social systems, our built environment and our natural systems, what currently exists and what happens when they're exposed to much more hot weather or a record event? What coping mechanisms do all of these things have? And is it then a hazard or a disaster? What's the impact? Does it exceed a society's capacity to absorb that impact? And then what can we do to either mitigate the potential for that impact, for that hazard to be high again, or to prepare better to reduce our vulnerability the next time? So that's the basis on which the work for the Annex 80 is happening. And one part of that was looking at disaster risk management processes, and one of the first things that disaster risk management professionals do is to try to understand the nature of the hazard. So if we think of the hazard as being a temperature hazard, which is both extended periods of high temperatures as well as heat wave periods, we need to understand the predictability of the hazard. Is it regular, irregular, outside of experience? The origin of the threat, the spatial distribution and temporal distribution of the threat. For example, a heat wave in August in southeast Queensland has a completely different impact than a heat wave in February, for example. A heat wave at night has a different impact to a heat wave during the day. The speed of onset, is it sudden, rapid, or is it prolonged? The scope and magnitude of the impact, and the number of threats. So an example of this would be if the hospitals are currently full in dealing with people with COVID-19, what happens if we have a heat wave at the same time? What happens if New York has a heat wave next week, for example? Or what happens if we have a heat wave after the bushfires or after a cyclone? So the first bit of research from this Annex 80 has determined that resilient cooling requires a number of fundamental things. First, that strategies for cooling must start with individuals or communities as active agents to be able to manage their cooling needs. Second, that the building is meant to protect individuals from heat exposure. Therefore, buildings' resilience to temperature hazard needs to be defined, and that's not done in any building regulations at the moment. That the limitations to the ability of cooling technologies and energy systems under different temperature conditions need to be quantified and communicated to end users. That strategies need to satisfy sustainability, energy efficiency and greenhouse gas reduction goals, and we need both quantitative and qualitative indicators. And one way of representing that is this multi-scale resilient cooling framework that's been developed. So trying to understand that for resilient cooling, we need to understand the energy system. So this is both the cooling technologies and the energy systems on which they rely and the buildings. We need to understand the environment system and the socio-economic system. And we need to understand these systems at a local scale, a regional scale, and a global national scale. And these are some ideas of some of the types of things that might help us understand what KPIs we need. So it might relate to kilowatt hours or cooling effect, or peak demand or network reliability, or ease of use or cost or availability of a technology or a particular building product, finance and insurance, global warming potential, carbon intensity, etc. We also need to understand what resilience means to populations or people. So when a person, a family, a population is exposed to a heat or a temperature hazard, their resilience depends on individual factors such as acclimatisation, physiology, behaviour, as well as environmental factors such as health policies, the communities and buildings in which they live. And these things impact on how well people can respond to an event, which then determines their resilience and how well that society can recover after a temperature hazard in order to be able to increase their resilience and their capacity to anticipate risk before the next temperature hazard. So as part of that, so addressing both of those things, both the renewable energy, energy efficiency and HVAC integration, and the need for resilient cooling are some of the reasons for the Living Labs. And the Living Lab project, the Living Labs are based a fair bit on the USA Green Proving Grounds, and you can Google the address for those. In this program that's been operating since about 2012 in the USA, government buildings are offered to suppliers of new and emerging technologies to be able to have their technologies independently tested in a live building. And the technologies that are offered for testing must fall into one of these 6 categories. And the things that are being tested, and the tests are often carried out by either Oakland or NREL, for example, some of the national laboratories, things like efficiency, load shedding, load shifting, efficiency generation and storage, etc. So, in essence, what all of this background research is showing is that we need to go beyond our traditional key performance indicators of kilowatt hours per square metre to a number of different things. So there's a range of things from a renewables energy efficiency perspective that we might look at. There's also a range of things from a building and people's resilience point of view that we might look at, such as passive survivability, etc. And what does this, so these are the types of things and the context under which the living labs are established. So what are the living labs? 2 living labs in Brisbane. The first is the Queensland Children's Hospital precinct. This precinct has 3 main buildings. The main hospital has 19 levels, about 112,000 square metres, and the main HVAC systems in this building depend on which part of the building the HVAC is supplying. So constant air volume systems for critical departments that have fairly even thermal loads, such as operating theatres, for example. Variable air volume systems for load varying spaces, so this tends to be the open reception areas, clinic spaces, etc. And active chilled beam system for the wards that are supplied with 100% fresh air. There's also a number of packaged air conditioning systems for non-clinical areas such as the kitchen. The second building on this precinct is the Centre for Children's Health Research. This is a 9-storey building with 5 stories dedicated to research labs, such as wet and dry labs, a gait lab, nutrition lab, and a tumour bank, and other services, including facilities management, reception offices, and a COVID-19 testing area on the other levels. The main HVAC systems are CAV, VAVs, etc., supplied with chilled water from the energy plant. The energy plant, the central energy plant, is the 3rd building on this precinct. The main plant details are listed on this slide. So the cross-flow induced draft cooling towers, the chilled water plant, the central heating hot water plant, steam. So notice that the heating hot water and the steam are both from gas steam boilers. Stormwater treatment and reuse, chlorine dosing, the standby power plant, so the diesel generators. So the hospital can run at full service with these diesel generators. And then their connection to Energix's network via 3 11 kV cables. Notice that the building was built with a tri-generation system, but that system was decommissioned, I think it last powered up in March 2019, because of the cost of gas, it couldn't compete with the cost of electricity that the government was able to negotiate through a power purchase agreement. We've been looking at the energy use of that precinct. So this graph is showing for 2019 for each month, the electricity consumption in kilowatt hours for the energy plant building in blue, the main hospital in orange, and the research building in grey. Notice that the research building, as you would expect from this type of building, has a fairly constant load. The hospital slightly varies. We don't know, we haven't correlated this data with any patient number data, for example. The biggest variation is, as you would expect in this precinct, in the energy plant, because it is the energy plant that provides the chilled water and the heating hot water. This is a Sankey diagram of the energy flows at the precinct for, I think it was February this year, showing how the grid electricity and the diesel and the grid gas are distributed to various sources around the hospital for various purposes. We've also been looking at the monthly peak demand. So for 2019, the months of the year are across the bottom. Notice that the peak demand in February is significantly higher than the peak demand in July, which indicates that a lot of the demand is seasonal. So having ways of being able to flatten that demand is one of the goals of the research that will happen there. The second living lab is being established at Fernhill Residential Aged Care in Qd. So this is a new building on a brownfield development, so an existing residential aged care precinct where some older buildings are being replaced with more modern state-of-the-art accommodation. So the new building currently under construction and due for completion around the end of June this year will have 144-bed residential aged care on 4 levels. So each level is much the same, 36 beds, and the rooms, average rooms are 26 square metres, larger rooms 35. All rooms have en suites. There's 18-bed dementia wing. Then this site has residential facilities, communal dining areas on each level. So each level is set out more or less on 2 wings that act much like a neighbourhood. On the ground floor, there's reception area and management training and consultation rooms. In the basement, a commercial kitchen and laundry that is expected to cater both for this whole building and future supported living apartments. Workshop, basement facilities, future day therapy and daycare areas, and also some retail spaces because this building is in King Street, Qd, directly opposite a major shopping centre, next to a school, etc. So wanting to integrate residential aged care with the general community. Some of the features or energy efficiency and or sustainability features of this building, it has been designed to be a hybrid building design. Ceiling fans and operable windows in all occupant rooms, really airtight building envelope, infrared sensors, LED lighting and sensors. For the first time for Bolton Clark, a building management system, and that will be for the HVAC system for lighting and sub-metering of electrical and chilled water loads, as well as an on-site weather station that might allow for some predictive control mechanisms. And the site has been set up to provide for future renewable energy and power factor correction. The site, this particular building is on a larger site that also has other buildings relating to residential aged care and a retirement village. So some potential for precinct energy trading also exists. The HVAC plant has been designed to have a peak design load for cooling. The 3 chillers, screw-type chillers, electric chillers, have been selected to enable either one small chiller to be used if required in the shoulder seasons, and 1 or 2 of any combination of 2 chillers to be used to enable for the variability in the cooling load because of the seasonality at Qd. The chilled water and heating water pumps are all variable speed. There's chilled water storage, heating hot water buffer tanks, variable speed, secondary chilled water pumps, etc. As part of, so the Living Lab can do some monitoring and testing of the whole building and of the whole site, but we've also nominated some occupant rooms to be part of the laboratory, in essence. So the building is roughly a W shape, and we've selected 6 rooms on the northwest wing of the W, which provides us rooms that have east, north and west orientations, all orientations that can impact on the heat load entering a building. We've selected a floor that is sandwiched, that has identical rooms above and below it, so that we can implement a change in the middle floor of rooms and compare that with the control rooms above and below. And in those rooms, we have a range of different sensors, from automated logic, from Steinel, that allow us to measure and monitor temperature, relative humidity, CO2, motion, air pressure, VOCs, presence, movement, and lux and sound, as well as some wiring to enable control of reed switches and control of openable windows and the air handling units supplying for each room. Because this new building will be, once this building is completed, the residents in the existing nursing home and hostel will move into this new building. So we've been monitoring the energy use of the existing nursing home and hostels to look at the range of kilowatt hours per bed per day currently. Then looking at the consumption over various years as well. So one of the things we'll be able to do initially is to compare the energy consumption of the same set of residents, more or less, or same number of residents, but all that's changed is the building that they are in. Currently, for the Fernhill site, again, as we saw earlier with another graph, that there's a difference in the profile of a peak summer day compared to a peak winter day. Winter days tend to have early morning peaks, but notice that the peak in winter is lower than the summer peak. The summer peak days provide a pretty good match, I think, to the potential for renewable energy. So what does all that mean regarding Living Lab test options? So this is not a restrictive list, but just a potential ideas list that at the hospital, at QCH, they're interested in things that might reduce the building heat loads, HVAC efficiency improvements, control optimisation, model predictive control solutions, precinct renewables, energy trading, power purchase agreements, that type of thing. At Fernhill, the options might include things that relate to natural ventilation and adaptive comfort, which might be things like smart controls of the operable louvers and blinds, etc. So sensors and controls, predictive control, but also precinct level renewables or storage or trading, for example. So if you're interested in any of those, some of your options are to contact either Aaron for the hospital or myself regarding Fernhill, or look on the iHub website. The team of people at QUT who are working on these things, so the information that we've presented today, I want to acknowledge the work of Aaron as the project manager for the hospital, and our team of Yunlong, Nima, Kayvan, Sharif, Glenn and Talara. So I'm open to questions now, and I'm just going to stop sharing my screen so I can see your faces. So any questions, please feel free to unmute your mic and I'll answer what I can, and I will ask for help from any of my team if I can't answer any of your questions at this stage.
Hi Wendy, this is Marty Gallagher. Can you hear me?
It's very soft, Marty.
Oh, okay, I'll talk louder.
That's good, thanks.
Okay, you've only been talking about carbon dioxide emissions, but I've recently heard and been very surprised that anesthetic gases like nitrous oxide and fluorinated hydrocarbons, like desflurane and sevoflurane, have a very, very high greenhouse warming potential, and that these anesthetic gases can account for a very significant part of the total greenhouse emissions by a hospital. Have you considered that in your analysis?
We haven't considered that in our analysis, because this particular project with the ARENA funding is relating specifically to energy consumption and the operation of these buildings, in essence. But I know that the first report that I presented right at the beginning, which is from the something like the International Green Healthcare Alliance, or I've just forgotten their exact name, certainly the greenhouse effects of medical gases is part of their remit to try to address. It's just outside of our scope of works because it's not something we can address with our current funding agreements.
Thank you, Wendy. It's Jenny here. Can you
Jenny.
hear me?
Yes, thank you.
Wonderful. I was just interested to see, given your central energy plant and the number of equipment that were on there, and how all of that has been managed within the BMS for those systems. Is there one BMS that managed them all, or is it multiple BMSs and so forth?
Yeah, so the hospital has one system that manages the thermal system. So the HVAC system is managed by one system, but other hospital systems are managed by various other systems. So there is not one integrated BMS for all the hospital systems at QCH, as there might be in a more recent hospital, I think Sunshine Coast Hospital, for example. So the lighting and other services are not managed by the same system as the HVAC system at the hospital.
Okay, thank you.
Are there any further questions? I must have done a really good job of it, or I've either bored you all and put you to sleep, or I answered all your questions, you have nothing to ask. So the aim of the Living Labs is for us to be able to test some emerging technologies. So at the hospital, for example, we've been speaking with, I think, 3 different technology providers now that think they have a product or a solution or a process that could help improve the energy productivity of the hospital. And we're working on developing now the test procedures and the requirements for testing those particular technologies. So it might be things that improve the heat rejection capability of the cooling towers, for example, or technologies that reduce the heat gain entering in through some parts of, some specific parts of the building, and that therefore then reduces the air conditioning load. Any questions?
Wendy, this is Frances. I was just wondering, so how old, in the aged care facility in Fernhill, that's going to be a new facility when that is built. How old is the hospital? Is that also quite new, or?
Yeah, the hospital was commissioned, I think, in 2013 or 2014. It's relatively new.
Yeah, okay.
Aaron, can you remember?
I think Francis was asking about Fernhill.
Oh, no, the hospital. So Fernhill isn't built yet, so that's going to be built. So that'll be a completely new facility.
Yeah.
Is that right? Yeah.
Yeah, so one's completely new and one is relatively new.
Mm-hmm.
They both have a lot of good energy efficiency things already.
Yeah.
But they can both improve, and for both of them, there was limited attention right at the design stage as to what can renewable energy and the control of HVAC systems sort of do. Not many buildings consider the integration of the control of those things, and that's one of the main focuses of these living labs, is to look at how to have integrated solutions rather than just energy efficient HVAC, good efficiency or good performance renewables, energy storage, etc. What are the benefits we can get from better integration?
Okay, so currently the hospital doesn't have any renewable energy?
The hospital doesn't have any on-site renewable energy because its capacity for renewable energy on-site is very limited. Right. For example, it has a helipad on the top floor, and the design of the building, green space, etc., for occupant health. So there's limited capacity for on-site renewables. But in their power purchase agreements, they are currently 15%, I think around about 15% renewable energy electricity supply through their PPA. But there are options perhaps for increasing the percentage of renewables in their PPA by having by being able to vary the hospital's load to better match where their renewables might come from, or to have some trading in the larger precinct around the hospital for renewable energy. So there's a range of options, and the potential perhaps for some energy storage, some electrification of some of the gas supply systems, etc. So the hospital itself is very unlikely to ever be on-site renewable energy powered, whereas Fernhill, that might be a possibility, because it all depends on the load profile and how much land and space you have available for renewables.
Right, so quite varied, list of options and solutions.
Yes, yes, yes. And that's
Great.
the thing, is to investigate different options that are suitable for different places. There's no one size fits all. So when we test some things in these sites, we'll be able to say this particular technology or solution is really good for this type of building, for this type of climate, under these conditions, but under other conditions, you might need to, think of these other variations, etc. So part of the testing and the extrapolation of the societal benefits is using models and simulations to sort of say, well, if we then did the same thing out at Bendigo or Toowoomba West or Charleville with a different sort of building shape, etc., you would get different results, but this is what we think those results will be.
That sounds great, thanks.
Any further questions? So like I said, so we're working with the hospital now, or with a number of potential technologies that we hope to start testing a little bit later this year at the hospital. For Fernhill, the building construction is still going slightly ahead of time. It's expected to be finished in June with the occupants moving in around late July. So we expect to be commissioning and testing all of the systems around about that time, around August, September, ready for doing our first round of testing of technologies for the upcoming summer. So if anyone's interested in things being tested, or if anyone wants to be involved in the International Energy Agency work, etc., we're happy to speak to you and either contact us directly or through the iHub website. We have a chat. Okay, great. Thanks, Ash. No, if there's no other questions, so again, a copy of the presentation and the recording will be made available as soon as I supply it to Adriana to get it up, and then we'll link that also to the iHub website, so it's all free to disseminate to whoever you think might be interested in it. I might just point out also that part of the iHub, the Living Labs, is also wanting to fully engage with the healthcare industry. So if you're in the healthcare industry and want to be part of an industry reference group to advise on things or help provide access to data, etc., where I'm happy to talk to you. So thanks everybody, and thanks for participating today. See you all later.